Okay, so today we're going to talk about hardware design with Python, so specifically digital hardware. And really what we'll eventually get to is we'll talk about a package. It's called MyHDL, so it's a Python package. So when I submitted my proposal, I was asked, well, what are we going to learn? So kind of giving a conference like this, there's people with all kinds of different backgrounds. So I kind of restructured what I originally had thought for my talk, and thought I'd kind of go through some of the basics. Really just review what is a computer, what is a CPU, and try to explain what programmable hardware is, and then how we program that hardware with a hardware description language. So this will be kind of a long trip in a short time, but hopefully it'll be interesting. Hopefully everyone will learn something. A lot of times when we talk about hardware, we talk about this time-space continuum. On one end, we'll have hardware that takes up not necessarily a lot of resources as in logic resources, but will take more time. And on the other end, we'll have something that might take more resources, but will take less time, depending if you're comparing the same operation. So I'm going to kind of be referring to this time-space continuum a little bit. So first, we're going to talk about time. We're going to talk about a computer and a CPU and kind of look at what that is. We're going to just develop a simple model of a computer so that we can compare and contrast it to our actual hardware. So hopefully this will give us a good understanding of everything that we want to figure out. So in computer organization, I'm going to break this into three components. We have our central processing unit, our memory hierarchy, and our I/O system. Now, the I/O system, there's a whole lot in there. There's your user interfaces, your video, your complex communications, wireless, Ethernet. We're not going to talk about any of that, but we'll talk about the central processing unit and the memory hierarchy. So the CPU is where all the instructions are executed, and the memory hierarchy is where everything's stored. So this is my simple model of a computer that I'm going to use for this talk. So what is that? Your guys' left, we have the memory, so the red block there. And this is an abstract memory. Right now, this is talking about caches, our main memory, our RAM, everything that might be in our computer model. And then on the right, we have the green box is our CPU. So this will fetch our instructions, it will load and store our data, and we'll load and store it into local storage, and then we'll execute the instructions and work on the data. I think everyone hopefully feels fairly familiar with that, and that makes sense. So our memory, we have a memory hierarchy. So we have cache, which is memory that's fast and close to the processor. And we have our physical memory, which usually is our RAM. So if you have a laptop, it has 8 gigabytes of memory or 16 gigabytes of memory. This is our physical memory. It's probably really hard to see down here, but we also have virtual memory, putting that under the category of I/O, because it really involves your OS and it involves complex communications to hard drives, etc. And then some people will put registers. Registers are hardware storage under memory as well, but I'm going to say that's actually part of the CPU. It's not memory, but it's just storage that's part of the hardware. This is a picture of a die of an AMD quad-core processor. The reason I put this up here is in a processor, in a computer, I wanted to outline how important memory is, right? So we need the memory to store in instructions, and we need the memory to store all our data we're working on. These outlined areas are the memory. These are the cache memories. These in the corners are the processors. But you can see that the memories take up more real estate than the actual processors. And I think this is a little bit deceiving too, because we have our L3 cache and our L2 cache, but I think our L1 cache is actually in the processor here, and we don't see the actual cache controllers. But our memory take up quite a bit of space in our computer hardware. Now, as I'm talking about these CPUs, there's more to them than I'm talking. I'm going to talk about a very simple CPU model. It fetches an instruction, it gets some data, and it executes one instruction at a time. But there's more to an actual CPU than the model we're kind of going to talk about. There's pipelining, hyper-threading, multi-core, complex I/O, a bunch of stuff. So for this conversation, we'll just ignore all that stuff. Okay, so if we look at a CPU, we have this ALU. The ALU is the arithmetic logic unit. And so we saw from the previous picture, we'll have hardware that will load, that will fetch instructions and load and store data. Now when we actually do the execute, that's what will present the data and the instruction to the ALU. So here we're going to present 3 and 4 to the ALU. We're going to have an instruction that's an add. The ALU, if it's working correctly, should output 7 if I do my basic math correct. In another example, it'll fetch another instruction. The instruction here will be greater than. And so we're going to say, is 3 greater than 4? We're going to say no, so we'll just output a 0. But there's also flags in the ALU that additional follow-on instructions may use. Now, the point of going through this is when we start talking about programmable hardware, I want to be able to have this in mind so we know how programmable hardware is different. So if we write a program, so if I want to write a program for this mathematical expression up here, this is just a sum of products. We're going to take we're going to take 2 lists or 2 arrays and just walk through and multiply 2 numbers together, and then we're going to sum them all together. So in Python, I can write this function like this. Now this is hopefully it's very readable. We're using lists or list comprehensions here to actually do this, to create a new list of the multiplies and then sum that list together. But these couple lines of code will turn into many lines of Python bytecode. So if I actually could use the Python libraries to disassemble that function. And so this was actually so on the left there, that's the disassembly of that function we just looked at. And that will run through the Python virtual machine. And the Python virtual machine is actually compiled down to machine code. So this is just an example. This is actual machine code, but it's not the Python virtual machine code. So the Python virtual machine code, once it's compiled down, will be executing the bytecode. So these are the low-level instructions that are actually presented to our CPU, to our ALU. So there's many, many instructions that are executed for a couple lines of our code. And it's pretty fortunate that we have pretty powerful computers that operate fairly fast. We have fast memories that all this can happen pretty quickly. So working with this example a little bit more abstractly, but if we look at a period in time, the instructions that are presented to our CPU, we'll load some data into some registers. We'll call them register 1 and register 2. Then we'll do a multiply instruction. We'll multiply that data. We'll store the result to some local storage in the CPU. Then we'll accumulate. So these are the instructions that are presented to the actual CPU. Now these are a little bit abstract. The actual instructions probably will vary depending on what your processor is. But this is what will happen. And depending on where the data is, there could be a lot more going on. Okay, so that was my quick review of computer architecture. So hopefully that will kind of get us, just set a baseline for conversation of that. And so when we're talking about the CPU, we're talking more on the time side. So we're going to take a little bit more time, and potentially we're going to use less logic, but we'll also be using more memory. Now let's look at the space side. So the space side, this is going to be my transition into talking about programmable hardware and how this will differ and look different than the kind of our computers that we're used to. So if we take the same problem, we have our sum of products. If I do this in hardware, instead of doing one thing at a time, I'm going to do on a multiply, then I'm going to do an add or an accumulate, a multiply and an add. I'm going to do this all at once. I'm going to put down a whole bunch of multipliers. I'm going to put down a whole bunch of adders. And when I present the inputs, the values here, in a very short time, I'll have the results. So this is a very different approach than kind of doing the instruction one at a time. I'm going to create some hardware that will do this operation and essentially instantaneously. But there's limits to this, right? Depending on the number of inputs that we have, we have limits on resources. So this can only get so big. So programmable hardware is usually, for digital programmable hardware, is in a field programmable gate array. So this is how we could achieve something like the previous slide is that we can build a whole bunch of multipliers and a whole bunch of adders, or use the multipliers and adders that might be in the device. But in the upper left-hand corner, we have an array. And so if we look into, zoom in a little closer on a part of the array, we see this grid here. In this grid, we have a bunch of programmable logic blocks. Those are the white and the one blue block that I have there. And we have a bunch of routing lanes. And in connecting those routing lanes, we have switches. Now, this is how we can actually program. We have this programmable logic block that we can program the logic that is executed in this block. And we can program the routing. So we can program what's connected to what. So if we go back, so if we abstractly think about this, I can put a multiplier in there somewhere, then I can route it to an adder, and I can route that to another adder. Now, in kind of the traditional programmable logic, we'll have to build an adder out of a whole bunch of these lookup tables, these programmable logic blocks. But we usually have enough of these that we can do a whole bunch in modern devices. But we still are limited. Multipliers and adders can chew up quite a bit of our programmable resources. So more modern devices, programmable arrays, they'll have some fixed function, which we call hard cores in them. So we'll actually put hard multipliers and hard adders in those. And we do that because they're used so commonly, or the companies do that because they're used so commonly. And then in that case, we don't have to use our programmable logic to build an adder or a multiplier. So in this is an example how one vendor actually uses columns, and each column is a certain type. So we'll have a math, which will be multiplier and adders. We'll have another column that is one type of programmable logic. We'll have another column that's another type of programmable logic. Another column that's internal memory. So this is kind of what a modern programmable hardware device will look like. Now, I kind of went over this really quick on the other slide. So we have this programmable logic block, and so how do we actually program that logic? So here we have what we'd call a lookup table. So on the far left, there's the lookup table, and we can program what that is. So in this picture, I have a 2-input lookup table. And I can program what the outputs are. And so in this case, for every combination of inputs, I'll program what the output is. We don't really ever have to worry about this level of details. We actually design it much higher, but it can be useful to understand what's actually happening in the FPGA. Now, did anyone attend the lightning talks last night? So everyone can tell me what function that is that I've programmed into that lookup table. It's the XOR. There we go. So also we usually will have a flip-flop that goes along with our lookup table, or a couple flip-flops depending on the architecture. A flip-flop is a storage element. You can put, in this case, a single bit into it, and it will hold that bit. And usually it holds that bit until there's a clock. We'll connect a clock to this flip-flop, and that clock just runs at some rate. And we'll talk about this a little bit more. And it will hold that at the clock edge. It will change the value. If the input is different, it will change the output on the clock edge. And so it will hold that output value even if the input changes until the clock edge. And if the value is different from the output to the input when the clock occurs, it will transfer it to the output. I have an example that we'll work through, hopefully kind of beat that idea home. Is this difficult to see, this picture? This is just a specific vendor. So Xilinx makes FPGAs, and this is actually what their architecture looks like. Since it's a little washed out, I will skip over that. Okay, so we've talked about these gate arrays. We talked about how we can program the logic in it. We talked about how there's fixed functions in them, and there's also some memory. So if I actually have a design, and I've described a design, and it gets synthesized down to actual logic components, when I route it into a device, it might look like this. So I'll have some programmable logic functions, I'll have some fixed functions, I'll have some memory, and then the programming will tie these all together. So this is what we're actually doing when we program this programmable hardware. When we program these FPGAs, we're defining what the logic functions are, and we're defining how we connect these logic functions. And so we kind of just have a signal flow then. So we'll apply some signal at one point, and it will kind of just flow through the system. So this is what I consider on the far right. So we're using up more logic, but we're using up less time. But typically in FPGAs, we're limited by this, how much logic we can use, much more than we're limited by time. So if I have a program and I want to let that program run for 10 days, I might be a little impatient, but I can let it run for 10 days. It's a little bit easier to get more time in a processor or a computer. In a FPGA, you can't get the same amount of space as easily. So when we do FPGA designs, we kind of have to work in this time-space thing a little bit more. We might not be able to flatten out an operation that we want to do completely because it'll just use up too many resources. So we might actually have to think about how this logic is structured and actually have it take up a little bit more time and use less resources. So whereas a computer is kind of fixed. Once you have that computer architecture design, it's going to be fixed at a certain point. With FPGAs, we're always designing and kind of looking at these trade-offs. Okay, so that was my quick kind of review of what a computer, a CPU is, and that was my quick review of what programmable hardware is. So hopefully we kind of have an idea of the differences. And so when I start talking about how we design programmable hardware with hardware description languages, we have these images to refer back to. Okay, so now what I want to start talking about is hardware description languages, and specifically MyHDL. So MyHDL is a Python package, and it uses a lot of the features in Python to be able to do this kind of domain-specific hardware description languages. The MyHDL was created by Jan. It was created almost 10 years ago. At least that's when the first release on SourceForge was. I'm mainly a user. So Jan gets all the credit for all the hard work and design. So here I say MyHDL extends Python, but it uses all the tools that in Python to kind of create this hardware description language, to just create this domain-specific language. So the MyHDL package, it's Python. For people that program Python, that statement seems silly. For people that do hardware description languages, that statement's very important. So what does the MyHDL package provide? It provides a couple types. So we use object-oriented and create a signal, and we have an int bit vector. Talk about that a little bit more. It uses generators. To create these kind of microthreads. It's how we define this high level of concurrency. And it uses decorators, kind of the metaprogramming, to wrap these generators into something that kind of looks like a hardware description language and kind of makes sense for what we want to describe and what we want to do. Hardware description languages, typically the common ones work at the register transfer level. If you want to use the tools out there to be able to synthesize your hardware description down to a netlist. A netlist is just a description of what the circuit is. It's kind of like the corollary to assembly language. It's just assembly language tells you what the machine instructions will be, or a netlist tells you what the circuit and how the connections are. For your hardware description language, currently you're going to have to get to some level of the register transfer level to be able to use the synthesis tools and technology that exist. So register transfer level, it's event driven. We define this. We say when this happens, and it's going to be when a clock occurs. We'll talk about that a little bit more. Then we're going to do a bunch of stuff. We do instantiations. So we'll have a module. What I call a module. It's a Python function but I call it a module because it returns these generators, and it's in other HDL languages, calling it a module or entity is fairly common. Then we also have the hardware-specific types. Okay, so let's look at an example here. So we have a circuit. We want to create the circuit up here, or we have the circuit up here. And we have these registers. These registers are multiple bits. Well, it's easiest to think of those as integers, but they're limited in their range, right? So they're only a fixed number of bits. So the range that these integers can represent is limited. And so each one of these R1, R2, and R3 are some storage elements. So a value will sit in there until something happens to move a new value in. These two clouds I have here are some logic functions. We'll take some value in and we'll do some operation on these values. Now in here I have these three registers, and they're actually controlled by a clock. When you're designing an FPGA, typically what you'll have is a global clock that synchronizes everything in your circuit. This is done just because it's an easy way to define rules for the hardware so that we can work at a high level, have a nice set of defined rules, and have confidence that our hardware will actually work. So I have this little pictorial here that tries to walk through what this circuit is going to do. So at time 0, at reset, I'm going to have 3 values in my registers. Now I'm just representing these values with colors. So R1 has my green value, R2 has my light blue value, R3 has my dark red value. Or someone might want to call that a violet or something, I'm not sure. So I'm going to get a positive edge of the clock. Can everyone see this, or is it kind of washed out? So I have this clock signal here that's continuously going. So I'm going to get my very first positive edge of that clock. And what's going to happen is the output of R3, I'm going to transfer to R1. So now R1 has what was in R3. The output of R1 is going to go through my logic function A, which is actually going to create it's going to make it light green. And so R2 is going to have that light green value now. R3, so the output of R2 went through this A inverse function, and so R3 now has a dark blue value. Now on the second positive edge of this clock, we'll do the same thing. So R3 will go into R1. The output of R1 will go through the logic and will be in R2. So now we change the color again. R2 will go through the inverse logic and go in R3. And so now we've gotten back. So we can see here we've gone right through the logic. So this is kind of how we have register transfer level. So we're describing what happens between these register transfers. Does that make sense? Does anyone have a question? Okay. So now if I want to describe this, so using Python and using the MyHDL package, I want to actually describe what's happening. So I define a module, and I say I'll have a bunch of signals, and those signals will be my registers. And I want to say that when I always get this positive edge of this clock, I want to do something. So here I'll say R1 next will equal R3. R2 next will equal the R1 passed through this function A. Oh, thank you. R3 next will equal the A inverse of R2. So this is how in Python, using the MyHDL package, this is how we can define the circuit that happened. Now, as I mentioned, so right now we haven't really defined how big those registers are. They can be 2 bits, 100 bits, whatever our circuit, whatever our design may want them to be. And we actually tell by limiting the range of this int bit vector. So this int bit vector is a range limited integer. Okay, so here's, I can see that's kind of washed out a little bit. Here's kind of the anatomy of a MyHDL module. So it's just a Python function, but we pass in, we say ports and parameters instead of, for a Python function, we usually just call them arguments. But ports are going to be signals, and the parameters are just going to be things that will define how our circuits are going to work. The code that's outside the generators. So I kind of jumped to this. I said MyHDL uses generators and it uses decorators, but this will be a generator. You don't actually explicitly see the yield here. This decorator will create the yield for you, but this is a generator. And outside of the generators, you have what we call elaboration code. This can be any Python code here. Inside the generators, you actually have limited, if you want to convert this to an actual circuit, you have limited code that you can actually use in here. So talking about these generators, this is kind of, we consider these microthreads. So microthread is something that the hardware design is just highly concurrent. You have a bunch of things that are happening at the same time. So if you think about it from a programmer's point of view, you have a whole bunch of microthreads, and all these things are happening at the same time. But to define these, we really need something that's, I like how this has been described, that's cheap as a function. So our thread has to be as cheap as a function, and that's just what a generator is, right? It's a resumable function, and it maintains state, so it works out really good for modeling our hardware. So a MyHDL module, or the Python function, returns generators. And these generators are, we can think of them as these microthreads. And these microthreads will either be converted to the HDL that can be synthesized, or they can actually just be run through the MyHDL simulator. I don't remember if I actually said what synthesis is, but in synthesis, this is what we take is the same as kind of compiling. Some tools call it compiling, some tools call it synthesizing. But this is just when we take our hardware description language and generate that net list. Usually the net list is an intermediate representation, kind of a device-independent net list, but it's all the low-level primitives and how they're connected. So just kind of talking about this a little bit more, again, we can define our module. Here we use the decorators to define my microthread 1. Here I can define my microthread 2. Now here, this is where I define, I could just say A equals B plus C, or I could say C equals A, or C.next will equal A plus B. And then right there I'll say, here's the hardware that will eventually be generated is an adder. And then here I could say D is equal to C times 2. And now I will get a multiplier. Or let's pick a more interesting number. We'll say it'll be multiply times 7. Yeah, question?
I didn't understand what you meant by returns a generator.
So here we have a Python function, and what we return here is we're returning these generators. Right? So we're returning these functions, so kind of the handle or the reference to these functions. And then these will be used by the simulator if we simulate this with the MyHDL simulator. So in Python, you can just run the MyHDL simulator and simulate the hardware. Or it will use these to convert to an HDL, Verilog or VHDL that can be run through the tools.
So it is sort of like the adder or a multiplier or things like that. Is that like one of those modules? Is that what the generator does?
So the question was, if the generators create the models, the generators are the kind of the microthreads. Inside the microthread will describe the operation. So if we describe C.next equals A plus B, we're describing the adder. But I could put something a lot more complex in there if I need. And so that essentially will be our one microthread. So our one kind of block in our hardware. So we have a whole bunch of blocks in our hardware C. And maybe when we talk through this a little bit more, maybe it'll become clear. If not, we'll talk about it some more at the end. So the MyHDL package, as we kind of talked about, it provides these decorators to describe when something happens. So at an event, an at instance is kind of just when it's first created, run. At always, we'll give it some set of events to define it. I'll always sequential, always seek. We usually give it a clock. Always comb is combinatorial logic. This will just actually infer anything that's on the right-hand side we'll use as our event generations. Signals, these are how we provide deterministic communication between our microthreads that we're defining. And the simulator will execute all these microthreads. So the simulator will simulate what our hardware should do. Okay, so earlier we looked at the sum of products, and we looked at if we just wrote a Python function to calculate this sum of products. So we did the sum of products, kind of just assumed that we had a list of one set of values, and we had another list of another set of values. We wanted to multiply them all together, and then sum them all together. Now, if I want to describe this in hardware, we'll define our module. I'll just compute some values here. Just added an assertion just to make sure they're the same size. We have my always seek here. Sorry, that font probably doesn't show very well. And so we're saying always at the positive edge of a clock, we're going to go do this. And so here I'm actually computing kind of an intermediate value. We're going to actually walk through the arrays, and then we're going to assign our output to that sum of products. There's a couple things you'll probably note here. So here I actually made an explicit loop. If you're writing Python code, people tell you not to do this. When we're writing RTL, when we're writing hardware code, we actually need to describe it this way because we have to be able to pass this down to the lower level tools. So we're not going to kind of take another method of doing it and undo it and kind of find this loop structure. So in this case, if we think about the picture I had when we kind of started this section, we have a bunch of multipliers and a bunch of adders. That's exactly what this will do. It will say when I have this free running clock, when I get a positive edge of this clock, I'm going to do this whole calculation. I'm going to do all these multiplies and all these adds. And if I'm running slow, I'll be able to do it all in one clock cycle. If I'm running really fast, we won't be able to do this. Now when we're writing this, we'll be writing this in Python, and we'll be simulated in Python, and we'll actually see what our hardware is supposed to do, what it's functionally supposed to do. So we also write a bunch of code to verify that our sum of products. So here, I create our signals, I instantiate our module, I create a clock. Here I actually am just using the function also that we created, and we use this to verify that the outputs of this match the outputs of our module. And then I'm going to simulate how this hardware would run. I'm going to create a reset. I'm just going to walk through a couple of clock pulses, and I'm going to verify that I get the same results. Now this idea of modeling and verification, so we just looked at one way of verifying a circuit that we described. These are very powerful features of using Python and MyHDL for a hardware description language. When we're modeling, there's no restrictions. We don't want to take this model and actually get it down to hardware. So if you're a hardware designer, you always want to do this. You want to take a design, a concept, and actually model it and start figuring out where the bottlenecks or where the issues might be. And so doing this in a language like Python and using a package like MyHDL is very powerful because you get to use the whole Python ecosystem. Excuse me. And that's also for verification. Verification is very difficult. There's a lot of energy and effort in the hardware side, the EDA industry, the electronic design automation, trying to come up with ways to create verification environments. With Python and MyHDL, you just jump to the end. You just have it. It's really nice. I've been able to use this in the work that I do and the hardware design that I do. This has been very powerful. You can also use you can do test-driven design. So you can use a lot of the frameworks that exist in Python. It's really, if you've designed hardware, if you've ever been part of or even had a little bit of exposure to it, this is very powerful. So when I was talking about this, we were always kind of under the idea that we're going to run this on programmable hardware, an FPGA. So I've kind of alluded to conversion, but I've never really discussed it. But in MyHDL, we'll have our descriptions, and we convert it to Verilog or VHDL. This is just a practical, pragmatic way to achieve what needs to be done, because we don't have a full synthesis tool, place and route tool in Python. So we need to convert it to Verilog and VHDL so we can leverage these existing tools. Now, the FPGA vendors provide these tools, these software tools. So your MyHDL description, your hardware description, will be converted essentially one-to-one to this lower level Verilog or VHDL. Now, it's not totally a one-to-one. The reason I say that is because you have this elaboration code. In the elaboration code, you can do any Python. So the code that's inside the generator that describes the logic, you can actually kind of prepare it in very powerful ways. So this is my complex view of the flow. The creator of MyHDL, Jan, he gave a keynote at PyCon Taiwan talking about the MyHDL package. He had a much simpler version of the flow, which is more usable than mine, but I like to make things complicated. But anyways, we have our Python environment up here. We have our MyHDL package. We're doing our RTL simulations. We're running the MyHDL simulator. We have our modeling, our verification. So this is kind of our front-end design. And then we're going to use the MyHDL conversion. So part of the MyHDL package, we have the MyHDL conversion. We'll convert our hardware descriptions to Verilog or VHDL. And at this point, we'll use the RTL synthesis tools. These tools vary from being expensive to free. I will create net lists, essentially gates. I've kind of have ignored what a gate is, but essentially we'll just create this low-level representation of what our circuit is. And from there, we can actually go to an FPGA or an IC. Now, MyHDL has been used to develop 6 or 7 integrated circuits, so actual hardware silicon. But most people will go down the path of using it for an FPGA. So now we can program an FPGA. So just before this, I kind of put the cart before the horse. We had a little workshop where we actually had a bunch of people sat down and we tried to program an FPGA and get the LEDs to blink. It didn't go quite as well as I would have hoped, but it was pretty fun. So this is the flow that we'll go through. So here's the FPGA tools. We just talked about they're provided by the FPGA vendors. Some are free, some are not. These are, for the most part, they're large, complex software environments. But it allows us to play with this technology. One of the things we also do with Python is we just automate the whole FPGA tool flow. So from a programming point of view, I just have a single button that I can push, and it will just compile, and I'll have something that I can load into the FPGA. I don't have to worry about the complexities of the design. All right. So in conclusion, I was hoping to basically introduce the MyHDL Python package, get a little bit of an idea what the hardware description is, hopefully inspire a little bit of curiosity. Also explain what a FPGA is. I don't think I really talked enough what you can do with a programmable hardware to say it's fun, but it can be fun. So hopefully this is fun and interesting, and people, if there's interest, we'll look into it. Here's some more resources. You can see Jan's talk on Speaker Deck. It's pretty good. Go to the MyHDL website. All the examples that we did in the workshop and some of the code from the presentation is out on this Bitbucket repository. So is there any questions?
How good is the OS support now for the proprietary FPGA tools?
So for the FPGA tools, they basically work on Linux systems. So they've always worked on a Linux system, and they work on Windows systems. And
how easy is it to mix those tools with Python or any other tool? You know, how easy is it to mix and match stuff? You know, thinking in terms of the shell. You know, how you mix all these little tiny tools to do interesting stuff.
Right. Unfortunately, it's a little difficult. So this is kind of what we worked through in the workshop. So we have From the Python MyHDL side, it's pretty easy. You install the MyHDL package, you can do your hardware descriptions, you can run a simulation, and you can see what the hardware will do. Now, actually getting the vendor FPGA tools installed and getting those all the way down to the circuit is difficult. Unfortunately, the FPGA vendors do not make these tools easy to install. So that's a little bit challenging, and you have to probably find someone that's done it before to kind of work through it, but that is a downside. Other questions?
Is there any way to create an image of the circuit or do a visual simulation in Python?
So from a waveform point of view, when you run the simulation, you'll get a bunch of waveforms, when the signals were going to 0, when the signals were going to 1. And so yes, when you run the simulation, there's actually a way to generate a waveform from that simulation. And there's a waveform viewer called GTK Wave that you can view all these waveforms. You can have an example in this talk that I've given, and I think in Jan's talk as well, there's an example of viewing the waveforms. So yeah, so I think that's one of the things that is nice about this is you can do this in Python. You can simulate your circuits and basically design your circuits and debug and verify them without worrying about all these other tool installations.
I have a question. How much support in MyHDL is there for directly communicating with all the vendor software?
In MyHDL itself, there's very little. I've put scripts together to just run the tools myself, and those are all open source or on a Bitbucket repository. You'll see them in my area if you explore there. Any other questions?
What's the coolest thing you've done with this stuff in an FPGA with or without MyHDL?
So for me, for hardware design and FPGAs, I've been able to do what I think is a lot of cool stuff. So I've built satellite communications, so modulators and demodulators in FPGAs. And this is actually where Python is really nice because what I used to have to do is I had to work in MATLAB, and then I'd go work in Verilog and VHDL. Now I can just do this all in one language, and it just works a lot nicer, at least from my perspective. I've also been able to build a couple ASICs, so actual integrated circuits for some medical things that have been really nice too. Really interesting.
You were doing your prototyping with the FPGAs, and then for production you went to the ASICs.
In some cases, and for the ASICs, we always did prototyping in the FPGAs, and like the satellite communication, the end product was actually the FPGA. Yep.
Just out of curiosity, how much does like an entry-level FPGA go for? So
a development board you can get from $50 to $100. You can get them fairly inexpensive. They're going to have medium size. They'll have like 10,000 programmable logic blocks, but you can do a fairly big design in those still. You could put a whole processor in there if you wanted. You could put a custom processor. You could put a small like software-defined radio in them.
So if I were to start working on FPGA, is there any resources that I can refer to? I don't know anything about from getting the board to starting with programming. So is there any online resources for that?
Yeah, there's a whole bunch. They're kind of spread out all over the place. But another attendee had told me about NAND to Tetris. Is that correct? Yeah, so NAND to Tetris is a pretty good tutorial that walks you through just looking at the low-level hardware and actually building a computer, or building a CPU. There's other. Is anyone familiar with EEV blog? So if you've ever seen that, he just did an episode on FPGAs that will kind of walk through in more detail than I did. It's roughly an hour long about just what an FPGA is. I have a blog on FPGA related where I'll put FPGA stuff, and I have some examples with MyHDL as just doing what I talked about yesterday, just doing the hello world for FPGAs and embedded systems, just blinking an LED. And I don't have my email on here, but it's chris.felton@gmail.com. Feel free to email me any questions, and I'll gladly help where I can. I I think that's about time.
Actually, you have another 5 minutes.
Okay, we have some more time. Any other questions?
You mentioned that the logic you can do inside the microthread is restricted. How do you know what you're capable of doing that could be translated properly?
So it's either going to be by experience or the tools will yell at you. So there is a learning curve. One of the things is when you go to learn hardware description language, so even using MyHDL, even though it's part of Python, there is a learning curve. You kind of, the MyHDL manual, Jan has done a really good job of kind of defining how you use MyHDL and what parts are convertible to actually get the synthesis. But there is a learning curve there. So you have to have a little bit of patience to work through that learning curve. So I alluded to a little bit, and I didn't talk more about it, but the convertible types, there's only so many types that will be convertible to the underlying, and those are the int bit vectors that are part of the MyHDL package. You can use integers, but they're going to be limited to probably 32 bits, depending on what the language that you're converting to. I think in both cases, it's just going to be 32 bits. You can use a Boolean, and that's about it. So you're going to have to use those types to be converted. But yeah, so you either just kind of experience learning it or just experimenting with it.
I feel embarrassed asking because I've missed most of your talk, but I'm curious, like in where would contributions be needed most right now on the project?
So contributing to the project, really, I think the biggest contribution is creating projects. So if you have a project you want to do, even if it's just a simulation environment, go create a project and simulate it, and then post it to the MyHDL news group. Actually get some hardware loaded onto there. The project has pretty good documentation, so I know some projects lack. This project actually has pretty good documentation. It'll always take more contributions. It has pretty good test coverage, but more test coverage is good as well. But I think it's really in doing projects at this point.
So your light bulb hello world example is posted up there? Yes.
Yep. The Hello World, the light bulb one is in this repository right here from Ohio. I also have some blogs that walk through some similar but slightly different ones. All right, thank you for letting me present.